Hi. Now I figured we would, having spent a fair amount of time on the Navier-Stokes equation, let's write it down again and look at a couple of important mathematical aspects, just one really, which has to do with boundary conditions. We've alluded to this earlier, but I figure it's useful to emphasize that a little more. So to begin with, let me write down the Navier-Stokes equation once again. Right. So again in lab coordinates in the Eulerian frame plus u dot del, this is the usual thing, and instead of writing the pressure term, the gradient of pressure on the right hand side with a negative sign, I choose to write it here. Yeah. This will be the body's force and mu, where I want to emphasize that this is a vector Laplacian. Right. Now, so a few things. So remember we wrote this down in a few different guises. One of the guises was one where all of this and this were all bundled together in one term, right, where but this is a slightly more popular way of writing down the Navier-Stokes equation, and this entire term, as we know, is the viscous term, and this is what in some sense makes it the Navier-Stokes equation. If this was not there, if the viscous term was not there, this thing is just the Euler equation that you've seen earlier, which does not take viscosity into account. The first thing you should notice is that if the viscous term was not there, this entire thing has only, these are all spatial gradients, right, these are all spatial gradients. These would look like d over dx or d over dy, no d square x over dx square, no second derivatives, only first derivatives, first derivative, first derivative, first derivative in, well, this these two are first derivatives in space, first derivative in time. So for the so what I mean is that the Euler equation only first space derivatives, right, that is evident, whereas the inclusion of the viscous term mu, this gives rise to second space derivative. So this completely changes the character of the equation. This is the main thing by way of boundary conditions. You have two derivatives, you need two boundary conditions, right? You have one derivative. You remember when we were talking about it's a different equation, but nonetheless when we were talking about this equation where this was the velocity potential, that was for inviscid flows. So it did not have the viscous term, but nonetheless the equation was this, and we had two boundary conditions, you remember? We had one boundary condition on the surface of the sphere and one boundary condition at infinity. Sure enough, you need two boundary conditions because you have two derivatives. Similarly, and so I just say that, and I won't confuse things, I'll just erase it here. Okay. So therefore, because you have two boundary conditions, therefore we need two boundary conditions on the velocity, not on the velocity potential, but on the velocity. Okay. For instance, you might, on the surface of an object, you might want to specify both the normal as well as the tangential velocity, or maybe the tangential velocity and the derivative of the normal velocity, or some mixture thereof. maybe a Dirichlet, in other words, a Dirichlet boundary condition or a Neumann boundary condition or a mix. Either way, you do need two boundary conditions. So, the inclusion of the viscous term changes the character of the momentum equation in this way, right. You would suspect this in any case, because you see, when we were talking about purely inviscid flow, you remember we were allowing for when we used the velocity potential and then derived a velocity from that, for inviscid flow, we allowed infinite slip, as much infinite, I will tell you what this means, of tangential velocity. Like so, if you have a sphere, and this we have drawn many times earlier, like so, and like so. Yeah, at the surface of the sphere, you were allowing the fluid to slip as much as it wanted to. Okay, and that is allowed only for inviscid flows. Okay, you need to specify only one boundary condition on the velocity. Okay, but not so for viscous flows. Now, this is intuitively obvious also, right. The whole point of viscosity is that the fluid sticks, infinite slip of the tangential velocity. This you cannot you cannot allow for as much of a slip as you want to. The fluid sticks. If it was honey flowing past a sphere, this is intuitively obvious, isn't it? So you would have to generally, you insist, generally you say that u normal as well as u tangential equal to 0 on the surface when viscosity is included. And you know this, for instance, on a fan blade, right, ceiling fans, you must have seen the dust sticks on the blades of the fan, right. That is because if it was and it all depends upon how smooth, the point is, air does have a finite viscosity, okay, even though it's it's mostly inviscid in the bulk flow, but as the blade accumulates oil or something, it does, air does have a finite viscosity, and when even though the blade is rotating, even though the fan blade is rotating, right on the surface, what happens is dust particles do come to a rest. Okay. In other words, the u normal as well as the u tangential are equal to 0 right there, and that is why you see dust sticking, okay, because of finite viscosity. Okay. It does not, if that was not there, the dust would be flying off the blades and you wouldn't have any dust accumulation whatsoever. But you know from everyday observations that dust does stick to the blades of a fan, and that is because of finite viscosity. Okay. So you do invoke, stuff does stick, and so this is one aspect that I wanted to emphasize, the difference between viscous flows and inviscid flows. I wanted to emphasize this. In fact, for inviscid flows, for perfectly inviscid flows, or perfectly inviscid flows which can be, or equivalently potential flows, which we have discussed, where u can be written as, this is a velocity potential, not a gravitational potential, u can be written as the gradient of potential. You can and this was the situation that we discussed, right, where now we are allowing for infinite slip, right. So we've written down, if this is so, then del square phi is equal to 0, and you recall that we wrote down the solution for phi and we applied the boundary conditions and got the particular solution for phi, right. Now, if that is the case, you can verify the following. You can apply, knowing the full solution for velocity, you can apply the having known u from phi, of course, yeah. You can apply the Bernoulli constant to get the pressure distribution over the entire surface. Okay. You can apply the Bernoulli constant to get the pressure distribution over the entire surface, and if you do this, so in other words, what I really mean is simply say, P, what I mean by this is P plus half rho u squared anywhere, yeah, is simply equal to P infinity at some very large distance plus half rho u squared, where u is this capital U is just the undisturbed velocity at infinity, this one. Okay. If you do this, and the P infinity, P at a very large distance is also known. If you do this, you can determine the pressure distribution everywhere, yeah. And if you do this, you will find that the pressure distribution is symmetric. In other words, there is no potential, you see, only if there is an asymmetric pressure distribution, the pressure in the front is different from the pressure at the back, or vice versa, there is some potential for drag, for a drag force. You see, the gradient of pressure is what gives you, a force, right? A gradient of pressure, this is like a force. If there is no gradient of pressure, if the pressure distribution is completely symmetric around a body, there is no scope for force. In other words, there is no scope, so therefore, there is no scope for drag. Okay. In other words, a sphere immersed in a perfectly inviscid fluid flowing past it, or equivalently, a sphere moving through a perfectly inviscid fluid does not experience any drag at all. And this was known, and this is opposite to everyday experience. You know that it takes a certain amount of energy, it takes a certain amount of effort to move a body through a fluid, no matter how inviscid it is, right. So, this particular thing was called the dAlemberts paradox. The fact that because the pressure distribution is symmetric, and that's simply a consequence of applying Bernoulli constant to the solution of Laplace's equation, which is applicable for perfectly inviscid flows, you find that there is no drag on the sphere, and this is called the dAlemberts paradox. And later on it was discovered that this is because there is no such thing as a perfectly inviscid flow. There is some sticking, there is always some sticking at the surface. You cannot allow for infinite tangential slip. Okay, there is always some sticking at the surface, there is always some viscous effect, and that is what gives rise to the drag. Okay. Now, going back, it is not as if there is, it's a little misleading to say there is viscosity or there is no viscosity. It is not exactly like that. It is just that whether the viscous term is important or not depends not so much on it does depend upon the magnitude of the viscosity constant, yes it does, but it actually depends upon this combination. Okay. So, if the nabla square u, if the velocity derivatives are very large near the boundary, then this term at the boundary, near the boundary, this term assumes importance in relation to, of course, this and so on and so forth. Okay. Far away from the body of the fluid, the flow might well be largely inviscid, or inviscid to a very good approximation, because there is not much scope for change in velocity, and definitely not much scope for second derivatives. Okay. So, the flow might well be inviscid in the bulk, but when it comes to boundary layers, when you're talking about layers that are close to the boundary that you're considering, this term, like for instance, the blade of the fan right there, or very close to this sphere that we're talking about, this term might well assume importance, and so this gives rise to the viscous term becomes important, and this was my main point. When you're talking about an equation with a second derivative in velocity, you need to consider two boundary conditions. Okay. And generally the two boundary conditions are simply the total velocity goes to 0, both the normal velocity as well as the tangential velocity. Yeah, both of these go to 0 right on the surface. So, this is the general sort of formulation. Okay. So, we will stop here for the time being.